from Universidad Nacional de La Plata. He's going to talk about families of induced trees and their intersection graphs.
Okay, thank you. Well, this presentation is motivated by an attempt to generalize the concept of click tree. So let us start with a brief summary about caudal graphs and the click tree. So most of you know that a graph is caudal when it does not have a cycle of length 4 or greater as an induced graph. There are many characterizations of caudal graphs, but the one more related to this presentation says that the graph is caudal if and only if it is the intersection graph of a family of subtrees as a tree of a tree, like in the example. So the meaning is that for every caudal graph we have a tree and we have sub-subtrees of it, such that two vertices are adjacent if and only if those subtrees share a vertex. This representation is not unique. If we are looking for a representation with the minimum amount possible of vertices, it is sometimes possible to reduce the number of vertices of a representation by contracting edges and the subtrees that have that edge. When we contract the tree as much as possible, it usually happens that each vertex of this tree corresponds to a maximal click of the graph. And because for every vertex of the tree, the subtrees that have that vertex will determine a maximal click of the graph, and conversely, every maximal click of the graph is of that form. So here is how the correspondence looks like. This way, the concept of click tree appears, and we can formally define a click tree as a tree such that the vertices of this tree are the maximal clicks of the graph, and such that for every vertex of the graph, the set C sub B of maximal clicks of the graph that contain that vertex B induces a subtree. So here, the tree with minimum amount of vertices, where each vertex corresponding to a maximal click is indeed a click tree of the graph. So what is our goal? The goal of this presentation is to find generalizations of the click tree. So I mean define a more relaxed version of a structure that is similar to the click tree, to try to describe and study other graph classes. We're interested in knowing if that is really useful or how complicated that can be. So let us start with a known generalization given by Gabriel, and it is about locally caudal graphs. A locally caudal graph is a graph such that the neighborhood of every vertex is a caudal graph. That means that a graph is locally caudal when it is free of wheels. A wheel is a graph consisting of a cycle plus a universal vertex. These are the first three wheels, but there are an infinity of wheels of any size you want. So the characterization given by Gabriel needs the definition of two acyclic family of subtrees. We say that a family of subtrees of a graph H is two acyclic when the union of every two of those sets is still a tree. It doesn't have cycles. So the theorem by Gabriel says that a graph G is locally caudal if and only if G is the intersection graph of a heavy two acyclic family of subtrees of a graph H. When I say family of subtrees or graph H, it means that H is not necessarily a tree. Well, we have sets that induce trees in that graph. There is a reformulation of this characterization that is more in terms of the problem that I am proposing here. we can also say that the graph G is locally chordal if and only if there exists a graph H whose vertices are the maximal clique of G, and such that for every two vertices P and W of the graph, again, when we consider the maximal cliques that contain those vertices, the cliques that contain B and the cliques that contain W both induce subtrees of that graph, and also the cliques that contain both vertices induce a subtree of that graph. Here is an example of a locally chordal graph and how that graph H can be constructed. Basically, as the graph is locally chordal, when we consider the neighborhood of every vertex, the neighborhood induces a chordal subgraph, so it has a clique tree. When we consider a clique tree for the subgraph induced by the neighborhood of every vertex, it always holds that we can take those clique trees or modify them to get another clique tree and fuse all those clique trees to get the desired graph H. So now we consider the more general question, and it is, given a graph G, is there a graph H whose vertices are the maximal cliques of G, and such that for every vertex B, the set of maximal cliques of the graph that contain B induce a subtree in H? When such a structure exists, we would call it a clique representation. It is defined as the clique tree, but in this case, I in H is not required to be a tree. So if we go back to the previous slide, we see that for a locally chordal graph, this structure exists, but it has an additional condition that when we consider any two vertices that are adjacent, the cliques that contain both vertices induce a subtree in the graph H. So if we want to be even more general, we will have to lose this condition, and that's really bad for us, because when we have chordal graph, we know that the intersection of any family of subtrees, when they have intersection, is a subtree. In this case, we will have sets that induce subtrees, but the intersection not necessarily is a subtree. So this is a limitation for our approach. So first, we can know that every graph G is the intersection graph of a healthy family of subtrees of a graph H. To see that, we can just take a bipartite graph whose vertices are the vertices of the original graph, like in this example, and the maximal cliques, where we make one vertex and one clique be adjacent just when the vertex is in that maximal clique. And the subtrees of this representation are just the close neighborhoods of each vertex of the original graph. So now, if we consider clique representations, it is very easy to see, for examples, that the wheel consisting of 4 vertices plus the universal vertex doesn't have a clique representation, because if there were such clique representation, it should have the edge C1, C2 because of this vertex. Similarly, it should have the edge C2, C3, C3, C4, C1, C4. But when we consider this vertex that is in all the maximal cliques, then the set C sub B for this vertex should contain this cycle. So a clique representation is not possible. But however, if we add a pendant vertex to this graph, now we have this clique representation. Because now this vertex is not in all the cliques, and having one additional clique allows to avoid the previous situation. So when we have chordal graphs being the intersection of subtrees of a tree and having a clique tree where equivalent conditions, but in this case, being the intersection graph of subtrees of a graph and having a clip representation are not equivalent conditions, because from the previous result, this graph is the intersection graph of subtrees of a graph, but it does not have a clip representation. Furthermore, we can note with these two examples that the property of having a clip representation is not hereditary, because this one has a clip representation and this one does not have a clip representation. So when we attempt to be general in the attempt to extend the clip tree to more classes of graph, we lose many useful properties that clip trees have. So in this context that is not favorable, now we could ask, what is the complexity of determining whether a graph has a clip representation? First, we will consider the problem of determining whether a family F of sets is the family of induced subtrees of a graph H. And well, as you can see here, that problem is NP-complete. To prove that it is NP-complete, we find a reduction from 3 sets. The construction will be as follows. We will take a formula in conjunctive normal form, and the sets are constructed as follows. For every variable p that appears in the formula, we will add the sets p with its negation, and an additional set that will have p its negation and 1/3 vertex p star. Now, for every clause R consisting of literals A, B, and C, we will introduce 3 vertices R1, R2, and R3. R1 will be in a set with the second literal of the clause, R2 will be with the third literal of the clause, R3 will be with the first literal of the clause, and additionally, R1 is with the first, for the start of the first literal, R2 with the start of the second literal, and R3 with the start of the third literal. We can note 2 things here. Because of these sets, we have that P is adjacent in P star if such a graph H exists, or the negation of P is adjacent to P star. But note both, because in that case a triangle would be induced in the graph H we want to find. Another important fact is that if such graph H exists, it cannot happen that A star, B star, and C star are all edges of H for any literal R that any clause R that we are considering. Because if that is the case, all the sets that we have in the previous slide plus these edges give a construction like this, and when we consider now this set, it will induce this cycle, so that cannot happen. So if we decide to make true those variables that are not adjacent to their star vertices, it happens that this will be an assignation of truth values that makes the formula that we have satisfiable. So this basically proves that the problem is NP-complete. And it is even well, I need to consider the converse first. Conversely, we suppose that there is an assignation of truth values that makes this formula satisfiable, and we will do something similar. We will construct a graph H such that the sets of the original family that had 2 elements will be edges of the graph, and we will also take into account that a variable will be true if and only if it is adjacent to the star vertex. Otherwise, well, when it is true, it is not adjacent to the star vertex. When it is false, it is adjacent to the star vertex. When we consider every clause of the formula, sometimes we see that more edges are necessary to add to this graph H. For example, if this is the representation graph corresponding to a clause, we have that the literal A is true because it is not adjacent to A star. B is true as well because it is not adjacent to B star either. And C is false because it is adjacent to C star. But when we consider the large set of the family, it will induce a subgraph consisting of the red edges, that this is not still a subtree. So we can always add edges between our vertices to complete the subtree. Well, now, yes, we can prove that this problem is NP-complete even when we consider Helly families. So let us consider any family F1, F2, until Fn, and we will find a Helly family such that the solution for this one is the same as the solution for the Helly family. To do that, we will add vertices U, V1, V2, and Vn. We will put U in every of the original vertices, and we will include each V sub I in the set Fi. Basically, the reason why we introduce U is to make the family Helly. Now all the F sub I have non-empty intersection at U, and these sets, V sub I, and any other elements and sets that I introduce later are with the objective that if this is a family of induced trees of a graph, then when we consider the new sets where all these vertices are added, one solution of the original problem corresponds to a solution of the new problem where the subtree induced by these sets are the same, plus in each F sub I, U will be adjacent to Vi, then Vi will be adjacent to some vertex of Fi, and the original vertices of F sub I will induce the same subtree that we can have in the solution of the original problem. When we know this, we can also prove that the problem of deciding whether a graph has a clique representation is NP-complete. It is a corollary. And the idea is we take a Helly family F, we add, if necessary, unit sets to make this family separated. Recall that the family is separated when given two elements, U and V. The family has a set that has U but does not have V. When we transform this family F into a separating family F prime, the solution of the problem of determining whether it is the family of induced trees of a graph is still the same because we just added unit vertices that do not add any problem because unit sets always induce subtrees in a graph. And now, if we consider the intersection graph of this family F prime, because it is Helly and separating the family, there is a property that says that for this intersection graph, the sets C sub B correspond to the sets of F prime. So there is a graph H such that these sets induce a subtree if and only if there is a graph such that all the sets here induce a subtree. But having a graph H such that all the sets induce a subtree is equivalent to having a clique representation. So as a conclusion from this section, we can see that it is possible to generalize the clique tree, for example, in locally corded graph, but not to a great extent. When we want to be even more general, many problems appear, and to make things worse, the problem of determining whether a graph has a clique representation is NP-complete, so that could make it difficult, possibly, to find a way to determine whether each graph has a clique representation. So, as a last part of the presentation, given the limitations that appeared in the first part, I propose to consider an intersection graph of subtrees of some particular graphs. So we have seen in previous slides that every graph is an intersection graph of subtrees of a bipartite graph. So we could consider intersection graph of subtrees of some particular bipartite graph. So we can start with this result by Serioli and Clark-Fitter, which prove the following, that these four conditions are equivalent. She is the intersection graph of a family of substars of a star. There exists a family, or there exists a clique C such that any two vertices outside C are either twins or non-adjacent. The set of simplicial vertices of G is a clique, or she does not contain any of the six graphs below as an induced subgraph. So note that stars are complete bipartite graphs such that we have a bipartition where one of the sets have one element. So thinking that way, we can introduce the following generalization. We will define for a bipartite graph the parameter mu as the minimum cardinality of a subset A such that A and its complement determine a bipartition. Again, let's call S the set of simplicial vertices of G, and now the property that we have is that the following three conditions are equivalent. She is the intersection graph of induced subtrees of a bipartite graph H, such that mu is less than or equal to K. She is the intersection graph of induced subtrees of a complete bipartite graph with the same restriction about mu. And the complement of G minus S has chromatic number less than or equal to K. And note that for the case that K is equal to 2, condition 3 means that G minus S is co-bipartite. That makes it possible to find a characterization of the class by forbidden induced subtrees. So it is basic that all antiholes C sub n with n greater than or equal to 5 will be induced subgraph. This is the list of forbidden graphs with no more than 8 vertices, where the dotted edges means that we can remove them and still have a forbidden graph. Then there are 13 more forbidden induced subgraphs with 9 vertices that can be formed considering what edges there are between the vertices U and the vertices D. And well, because of the restriction of time, I won't explain it, how it is constructed. So well, what could we do later? We could try to continue this path and consider more specific classes of bipartite graph and check what arises when we consider the class of intersection graph of subtrees of that bipartite graph. So that's all. Thank you for your attention.